Hello, how's it going? Hello?
Hello.
How's it going?
Good. How are you?
Good. I think this is the fastest I've been able to get Zoom to start working. Good. Okay, I'm loading up the slides. Okay, are you able to see the screen?
Yes.
Yes.
Okay. So the goal for today is to talk about how you would do combinatorial proofs. And I want to leave a little bit of time so you can talk about some of the stuff you're thinking at and trying for the gaps. I want to go over some of the problems that we had last summer. What did we look at? How did we try to solve them? What gave us trouble? What we were able to do eventually. And by going through these arguments, give you a little bit of a sense of how you attack research questions, what the techniques might look like, as well as how painful the algebra can become. So a lot of times the idea is pretty clear about what to do. And the phrase is, the devil is in the details. And to just get the algebra to work out right without making a mistake is a non-trivial task. And so today we will see a good amount of algebra at times. Okay, so let me start with the problems. So here's the stuff we were looking at last summer. So we spent a very small amount of time looking at gaps between summons and simple paths. So I had one person who looked at this just a little bit, but then moved on to something else, which is why I am giving that problem to you guys this summer. And it's not immediately clear what is the right definition to use for gaps, because now we're not talking about gaps between indices, which are just integers, but now pairs of integers. The other things we looked at was to try to find a combinatorial formula for the number of simple paths in many dimensions. We got an asymptotic for this last year. So what that means is as the size gets very large, we look at everything from, say, 0, 0 to nn, we had a pretty good formula for the main term. So if you took what the truth was and divided by what we got in the limit that converged to 1. But we didn't have an exact formula unless we were in 1 or 2 dimensions. I now think it's going to be very, very hard to get an exact formula for this. You are welcome to try to prove this, but based on the difficulties we've seen, I'm not optimistic about how accessible that will be. And then the big result from last summer was for d-dimensional simple paths, we had formulas for the mean number of steps before you hit the origin, the number of steps in your decomposition, the number of steps in your path, and the standard deviation, and we showed that it converged to Gaussian behavior. So we got that last year in the Eureka program, and then I continued working with this with some college students at Carnegie Mellon in the spring, and we were able to remove the simple assumption, and we can now work with compound paths. And so again, we have an asymptotic formula for the number of paths, and we have formulas for the mean, the standard deviation, and the Gaussian behavior. So is everybody comfortable with probability at the level of mean and standard deviation?
Yes.
Yes. Yes.
Okay. Is everybody comfortable with what it means when I say converges to a Gaussian?
Yes.
Yes.
Okay.
Yes.
Excellent. All right. So let's calculate the mean and the variance. What I like about this calculation is we had this several years before the Eureka program, and this calculation turns out to have been thwarting our efforts to generalize. And the reason is there's a really simple proof for the mean and the variance in 1 or 2 dimensions, and that elegance is gone when you get to higher dimensions. And so we were trying for a long, long time to get a similarly nice formula in higher dimensions and just couldn't. And so here's the formula. So if mu I denotes the mean number of steps in a simple jump path from I to the origin, then for each positive integer n, the mean of mu n plus 1 n plus 1 is a half n plus 1. And again, when you have a lattice path like this, you want to be clear as to where you're starting from. This is the simplest case, starting from the upper right corner. And it tells us that the number of steps on average is essentially half of the either horizontal or vertical component. They're both the same because it's a square. So this is a really nice formula for the mean, and it tells us that the mean is growing linearly in n. So let's recall the definition of the first moment. So the first moment is going to be the probability of taking on the value k times k and just summing over all possible values of k. Now, since we have to include the upper point n, there's going to be at least one step. So the number of points k is going to range from 1 to n plus 1. And then the notation from last time is Sn plus 1 n plus 1 is the number of paths starting at n plus 1 n plus 1, and T n plus 1 n plus 1 k is the number of paths of length k. So if I look at the T divided by the S, that's going to be the probability of taking a path of length exactly k. I multiply that by k, and that will be the formula for the mean. All right, so now this is the real reason I wanted to talk about this. It's how do you handle sums like this? And the goal is to do algebra. The hardest part is seeing what is the best way to attack these proofs. So why am I switching from k to k plus 1?
Because now you are adding up the sum from k equals to 0 to k equals to n.
Yeah, so instead of going from 1 to n plus 1, I'm going from 0 to n. But there's another reason why I want to do this.
Is it to keep the calculation more simple? Because we know like the coordinate for x and y is like n plus 1, so you want to change from k to k plus 1.
Yeah, I think that's basically it, is that it's going to just make things look a little bit nicer. And so going from 1 to n plus 1, we're going to go from 0 to n. The k plus 1 is going to go nicely with the k plus 1 over here. And now here's the point. When I expand the k plus 1, I'll have k times the formula we had from last time. So we had the number of paths was 2n choose n. And if we do tn plus 1, n plus 1, k plus 1, we actually had a nice formula for that. The number of such paths was n choose k squared. So this is why we really shifted to k plus 1, because the formula is a little bit nicer here. I've got a binomial coefficient with k. I would much rather have k than k minus 1 or k plus 1. And then I also have the 1. But if I have 1 times the t's, if I sum that over all k's, well, since the sum of the t's over s's is just 1, this is going to just give me the total number of paths. So the plus 1 is easily handled. That's just going to be the 2n choose n. And that's because when we sum over all the different t's, that just gives us the total number of paths, which is 2n choose n. So we have to figure out what is the sum of k times n choose k squared. Now, the other way you could have seen that the sum over the t's is 2n choose n is to use the binomial identity. The sum of n choose k squared is 2n choose n. Have you seen a proof of this result? Have you used this result before?
Oh, I think I have seen another version of this. Like, well, it's basically about like m choose 0 times like n choose n up to m choose m times n choose 0, and then if m equal to n, then the final result is like this.
Yes, and in fact, what you're using is that n choose k is the same as n choose n minus k. So I can rewrite it like this. And here's the story. Imagine you have 2n people and you want to choose n people from 2n. The number of ways of doing that is just the right-hand side, 2n choose n. Imagine we have n Americans and n Chinese. If we want to choose n people, if we choose k Americans, we have to choose n minus k Chinese. And then we just sum over all possible values of k. So this is a story proof of this identity. By telling the right story, we get it immediately. And so now we want to use the following identity to complete the proof. The sum of k, n choose k squared, is 1/2 n times 2n choose n. This is going to be really nice for us because now when we divide by 2n choose n, we'll get 1/2 n, and we'll get the plus 1 from over there. So all we have to do now is prove identity 3. All right, any questions on what we have so far?
Can you explain more how you arrive from like the sum of k equal to 0 and k plus 1 t n plus 1 n plus 1 k plus 1 over s n plus 1 n plus 1 to the thing on the right?
Sure. When k hits the t's from last lecture, t n plus 1, n plus 1, k plus 1 is just n choose k squared.
Yes.
So,
Yes.
so when k hits the t's, that gives us the k n choose k squared.
Uh-huh.
Now, when the 1 hits the t's, well, then we have the sum of n choose k squared. And the identity we just proved down here, it says that that's just 2n choose n.
Oh.
This part comes from. There's another way to see that. So one way to see that is to use this identity. The other way to see this is to say, well, look, s n plus 1 n plus 1 counts all paths. T n plus 1 n plus 1 k plus 1 counts all paths of length k plus 1. My path has some length. So if I sum the number of paths of length, k plus 1 over all k, that's going to just count how many paths there are. And we know that paths is 2n choose n.
Okay.
Multiple ways to get to the right-hand side of 2. All we have to do now is prove the identity 3. So again, what I want to do is I want to just introduce you guys to some really clever ideas on how to attack problems like this. So here's a great way to handle the sum of k and choose k squared. What we're going to do is we're going to write it as a sum k goes from 0 to basically n halves of k and choose k. And then we're going to write it as a sum k goes from 0 to n halves of n minus k and choose n minus k squared. Well, n choose k is the same as n choose n minus k. And if k goes from 0 to n halves, n minus k is just the values of k that we were missing because this sum should really go from 0 to n. So basically, for instance, if k goes n minus 5, well, just write it like this. And then we'll just use k as the smaller values. So is everybody comfortable with going from here to here? This part over here is just taking the values of k here that are greater than n halves. We're trying to use some symmetry.
Can you explain more?
Sure. So we have a sum k goes from 0 to n. Do you agree that the stuff over here is the first half of that sum?
Mm-hmm. Sure.
So now let's take a term in the second half. Let's take the term when k is equal to n minus 5. Well, that's exactly what this is going to be because k goes from 0 to n halves. So when k equals 5, that will give us n minus 5, n choose n minus 5 squared. That's the term when k equals n minus 5. So these terms here, the 0 to n, I split from 0 to n halves and then n halves. And the stuff in n halves to n, I can write it like this. I just write it as n minus k with k now between 0 and n halves. I really should have k between n halves and n, but by writing it as n minus k, I can have both sums over the same range.
Okay.
And it's very advantageous to have them over the same range because now you notice that the k and the n minus k combine and give you just n. And n choose n minus k is the same as n choose k. So the sum is just n times n choose k squared. So that's equation 4. Are we comfortable with 4?
Yes.
Okay, so now moving on to 5. By symmetry, the sum of n choose k squared is the same as the sum of n choose k squared, with the first time I go from 0 to n halves, and the second time from n halves to n. Now, we have to be a little bit careful, and if you notice, it says we assume that n is odd. Why am I being careful to assume n is odd? So why am I assuming n is odd in this?
Because when n is odd, the left part of the equation is equal to the right part of the equation. If it is even, it's not like this.
If it's even, they're still equal. Equation 5 is still true if they're equal. But there's a problem with equation 4.
Oh yeah, I'm talking about equation 4. So
Okay,
if it is even, like you will count. If it is like if n is 12, you will count when n is equals to 6 twice.
when k equals 6.
Yeah, when k equals 6.
I'm sorry, right, when k equals 6. Correct. So when n is even, n choose 2 is an even number, and we've now double counted the middle coefficient. It's counted twice here, but only once here. If n is odd, then n divided by 2 is an odd number. I'm sorry, is a half integer. And so we're not going to worry because that won't be a term. So you have to do the analysis a little bit differently depending on whether or not it's even or odd. It's not a huge deal. So from equation 5, we now get equation 6. That the sum that we want to do is just 1/2 the total sum. And this is really nice. We'd much rather have a complete sum. And the reason is we know that the sum of n choose k squared is just 2n choose n. And that proves equation 6, and that gives us the formula for the mean. So there's a lot of really good ideas in this proof. We were very proud of this proof. The problem is, it turns out this proof is very misleading. And the algebra miracles that happen here, we don't know a good way to do them in higher dimensions. You are welcome to try. We would love to see a proof that's elementary for the quantities. So now let's consider the case when n is even. So what we need to do is we need to just explicitly remove the case when k is n over 2, and then everything else we go to n halves minus 1 and n halves plus 1, and then we then play a very similar game. So it's much harder to do math on the spot and just read and process a lot of mathematics. What you want to be able to do is get a big picture idea. Do you understand roughly what's going on? And the idea is very similar to what we had before. We just have a little bit more bookkeeping to do. So this is really not that interesting here. It's really essentially the same as what we had before. And so again, we use symmetry of the binomial coefficients. We enter things, and now we just have to be a little bit careful because of double counting. And when the dust finally settles, we still get the same formula. just a little bit more work in the case when n is even. Okay, so that was the mean. So now the harder one is to calculate the variance. And then the next one after this would be to try to calculate elementarily any finite moment. In some sense, we don't need to do this because we have a proof of the Gaussian behavior, but it's nice to see what you can do elementarily. So the standard deviation is n divided by 2 square roots of 2n minus 1. So as n goes to infinity, what does this look roughly like? How does it grow, roughly?
It grows exponentially.
It grows, could you say that again? It grows what?
Exponentially.
So what does it mean to grow exponentially?
Just like growing very fast.
Well, growing exponentially would be like 2 to the n, or 3 to the n, or 1.5 to the n.
I think it grows more like square root of n.
It grows like square root of n. If n is very large, the denominator is approximately 2 root 2n.
Yeah.
So it looks like it's approximately the square root of n divided by 2 root 2. So it's going slower than linear. So the mean is growing like n, it's growing like n halves, and the standard deviation is growing like square root of n over 2 root 2. So that means the standard deviation is much smaller than the mean. And so it's going to look like most of the values will be somewhat close to the mean. So let's see how we would prove this. So by the definition of the second moment, there's a couple of different formulas you can use to calculate standard deviations. How many people here have not calculated standard deviations? Okay, so everybody's calculated standard deviations. Excellent. So there's 2 formulas you can use. You can use the expected value of x minus mean squared, or you can do the expected value of x squared minus the square of the expected value of x. Computationally, it's often a lot easier to use the second one, the expected value of the square minus the square of the expected value. We know what the mean is. That's the expected value. That's the 1/2 n plus 1 squared. And so this will be the standard deviation. And here I'm using k, not k plus 1. I haven't shifted things. And so we have an n choose k minus 1 because we haven't done the shift. Now we'll shift the index of the sum to start at k equals 0 and we'll expand. So this comes just from shifting. And now we write k plus 1 squared as k squared plus 2k plus 1. And that's why we have 3 terms here. Boom, boom, boom. This term over here, we pull out the 2. We have the sum of k, n choose k squared over 2 n choose n. That's basically just the mean. So we get twice the mean over here. And then we still have these 2 terms to deal with. Well, this term is not going to be bad. That's going to be essentially the number of paths. We got to be a little bit careful because we often have k plus 1, and here we just have a 2k. I'm not going to go through all the little algebra. Notice the plus sign is now a minus sign. The challenging part is to deal with the sum of k squared. So when we put in everything else, we'll have a minus n squared over 4. How do we evaluate the sum of k squared? So any thoughts as to how we might try to evaluate k squared and choose k squared? So this is a hard problem. How would we deal with the k squared piece? What do you have that might cancel the k squared?
You multiply k squared into the binomial coefficient.
Yeah, so it may not work, but another thing to try is the n choose k is going to give us an n factorial over k factorial, n minus k factorial. Maybe the k's cancel somehow. It's worth considering. we're going to use the following identity. K squared n choose k squared is n squared 2n minus 2 choose n minus 1. And so we'll prove this identity now. All right. And the start of the proof is exactly what you said. So terrific intuition. We start by replacing the binomial coefficient with what it is, a ratio of factorials. And the k squared is going to cancel with, the k factorial squared in the denominator. That becomes a k minus 1 factorial. We then have an n factorial. I'm going to pull out an n from it, and we'll get an n squared times this. So the question is, why am I pulling out an n squared?
So that the bracket on the right can be like a binomial coefficient.
Excellent. You always want to think, what can I try to write this to look like that will help me? And now that I have a k minus 1 and minus k, this adds up to n minus 1. So I really want an n minus 1 upstairs, not an n. So I'll pull out an n. What's nice is because n is independent of the summation, I can pull that whole term outside. And so now we shift indices, and we can rewrite it as n squared times n minus 1 choose L. And we can write that as very similar, because we're squaring things, as n minus 1 choose L, n minus 1, n minus 1 minus L. Well, we've seen this numerous times. This is I'm choosing n minus 1 people from 2n minus 2 people. And so it's just 2n minus 2 choose n minus 1. You always want to have a sense of where the formulas are coming from. Where is the miracle coming from? And so now when we substitute this in, when the dust settles and we just do some algebra, we'll get n squared over 8n minus 4. Okay. Any questions on the algebra up to here?
No.
Okay. We unfortunately could not find ways to generalize this to higher dimensions elegantly. So that's open, but I think it would be very, very hard. So what I want to do now is I want to talk to you about one of the most important methods in mathematics, differentiating identities. So the idea is, if you have a nice probability distribution, if you know its moments, you know its distribution. How many of you have seen Taylor series?
I did.
Anyone else, or just one? If you've seen Taylor series, if your function is nice, it's uniquely given by its Taylor coefficients. It's sadly possible to have two functions that have the same Taylor coefficients but are different. So the subject has some technicalities. But the hope is that if you understand the Taylor coefficients, you understand the function. Just like if we understand the moments, we hopefully understand the probability distribution. So differentiating identities is a way to create infinitely many new identities from an existing one. Since it's so hard to prove an identity, any way you have to generate new identities from it is almost surely going to be valuable. And one of the most common applications of this is in probability theory to find moments of distributions. Okay, so here is an argument. Tell me if this argument is correct. We take the derivative of the infinite sum. It's the same as taking the derivative of 1 over 1 minus x, because the infinite sum is just 1 over 1 minus x. The derivative on the left is just the sum of the term-by-term derivatives. The derivative on the right, just when the dust settles, is 1 over 1 minus x squared, because the two minus signs will cancel. And so I have the beautiful formula because I know what the derivative of x to the n is. It's just n x to the n minus 1. So what is wrong with this proof?
Can you explain again the algebra you have just briefed?
Sure. So the first step is the geometric series formula. X is less than 1 in absolute value. The sum of x to the n is 1 over 1 minus.
Oh, okay. Okay.
So I start with the geometric series formula.
Mhm.
Take the derivative of each term, of each side. The derivative of a sum is the sum of the derivatives. The derivative of the quotient, well, I use the quotient rule. And then the derivative of x to the n is just nx to the n minus 1. So where is the mistake, or where's the step that needs justification?
What's x?
X is just our variable. In calculus, we often use x as our variable.
Okay.
How do you get the second equation from the first one?
The derivative of a sum is the sum of the derivatives. And then the derivative of 1 over 1 minus x, that's 1 minus x to the negative 1. So it's negative 1, 1 minus x to the negative 2. And the derivative of 1 minus x is negative 1. So the two negative signs reinforce.
You didn't specify that x is between 0 and 1.
So I'll say right now, x is between 0 and 1, or negative 1 and 1. If you want it to be, it's a half and a half. So you're right. We need to have some conditions on x to use the geometric series formula, but I'll impose those.
Okay.
So one of the steps needs some justification. It's the derivative of the sum is the sum of the derivatives. You never proved that in your calculus class. What you proved is the derivative of a sum of two terms is the sum of the two derivatives. This is an infinite sum. How do you know you can justify interchanging a derivative with an infinite sum? It can be justified, but that is a bit advanced. And I like to show this to just highlight how easy it is to accidentally assume something and not be aware that you're doing so. It's so easy to feel, well, of course I can do this. No, we only proved it in the case when we have two terms or three terms or four terms. As a nice exercise, you can prove using grouping or induction that if you can take the derivative of a sum of a finite number of terms, say n terms, you can also take the derivative of the sum of n plus 1 terms, term by term. But that's the subtlety here. So this is the more general theoretical slide. I'm not going to really go into it, but just if you want, it's there. So here's an application. So let's go back to the binomial theorem. The binomial theorem says that the sum of n choose k, p to the k, q to the n minus k is p plus q to the n. So this is the binomial theorem. What we want to do is we want to generate more equalities from this. So the first thing is we're going to use the operator p d by dp on both sides. So if you haven't seen multivariable calculus, when you have more than one variable in play, you use the curly d like this to indicate it's a partial derivative. Hold every variable constant, but the variable that's involved with it, which in this case is p. Now you might say, why am I multiplying by p? Well, when you look over here, it's a little unsatisfying that we have nx to the n minus 1. If we multiply both sides by x, then we would have nx to the n. And it would just be a little bit cleaner. It doesn't really matter, but. So now, do I have to worry about interchanging a derivative and a sum here? So can I justify interchanging the sum and the derivative? Is it an infinite sum or is it a finite sum?
It's a finite sum.
It's a finite sum. The only issue is when you have an infinite sum. Because it's a finite sum, by doing grouping and induction, you can prove that you can do it. And so now when we take the derivative with respect to p, we'll get a k, p to the k minus 1 on the left, and a p n, p plus q to the n minus 1 on the right. And now if I multiply by p, the p to the k minus 1 becomes a p to the k. And on the right-hand side, I now get np, p plus q to the n minus 1. So this leads to a formula for the sum of k, n choose k, p to the k, q to the n minus k. The most common value for p and q is 1/2, but you can choose other values. And now what we want to do is we want to find formulas for the variance. So I've remarked a couple of times that there are two different ways you can do it. You can do the expected value of x minus the mean squared, or the second moment, the expected value of x squared minus the square of the expected value. And you see you have two different sums to evaluate. One is, a k minus np squared. The other is a k squared. Which would you rather evaluate, the first or the second?
The second.
Yeah, the second. It's much cleaner. There's no cross terms. We want to evaluate stuff like the second. So let's look at what we have. We know the sum of n choose k, p to the k, q to the n minus k is p plus q to the n. So we know applying p d by dp once gives us this. Let's apply it again. When we apply it again, we'll get another k coming down, and we'll get k squared n choose k, p to the k, q to the n minus k. Now notice the right-hand side becomes a bit more involved, but it's not too bad. Now is the point where life gets much better. Equation 24 and 25 hold for all values of p and q. Why is it good to choose q to be 1 minus p? So what's the advantage in choosing in choosing q to be 1 minus p?
So that p plus q equal to 1.
Yeah, so now p plus q equals 1. And the advantage of that is we're talking about a probability distribution now. So it's probability p of success, 1 minus p of failure. And notice that equation 25 becomes much nicer when p plus q equals 1. And now we get equation 26, which is exactly what we wanted. All right. So to just recap, the goal is if you have a nice probability distribution, the kth mean, the kth moment is just the integral of x to the k times the probability density. Or in the discrete case, it's n to the k times the sum of all the probabilities that x equals n. Okay. We're about to shift gears to the Gaussianity. Any questions before we come here? Okay, so the idea is we want to go through the algebra and show that it's a Gaussian. We have the mean, we have the standard deviation. The algebra will get involved, but it'll be a chance for us to use some techniques we've learned. All right, so this is just some numerical data. We want to show convergence to a Gaussian as n gets large. And we're going to look at simple jump paths, with k between 0 and n. So the densities is the number of simple jump paths with a fixed number of steps. So this was like a Tn plus 1, n plus 1, k plus 1 divided by Sn plus 1, Sn plus 1. The number of desired paths divided by the total number of paths. So we will study a square lattice, the case when a equals b or n, where you start off in a diagonal component. So the first theorem is that the mean on a square lattice is 1/2 n plus a half, or about n halves. This is true in 2 dimensions. We've done the proof. The question is, can you extend this proof to higher dimensions? The next one is the standard deviation on a square lattice. So it looks like it has a different factor of 2 on the bottom. The last one I thought we had was like a 2 root 2n. But it might just depend on how things are being normalized. So we've talked about how to calculate the standard deviation. And just you're going through it a little bit more explicitly. The density function, this is going to be the probability that we have a gap of length k plus 1. We count how many paths are there of length k plus 1 and divide by the total number of paths. And this gives you the fraction of paths that are of length k. So doing a little bit of work, simplifying the binomial coefficients of this monstrosity, we get n factorial to the 4th over k factorial squared, n minus k factorial squared, and then 2n factorial squared. Another key ingredient is Stirling's formula. And Stirling's formula says m factorial is about m to the m e to the minus m squared of 2 pi r. All right. So we can apply Stirling's formula to this expression we had over here. And so after the dust settles, after you do a lot of Stirling, you end up with this line. Fn plus 1 is the following. And now we want to try to understand how this behaves in the limit. So I'm going to write it, this density Fn k plus 1 as a Pn piece and an Sn piece. And it's nice when you look at this, you've got n's and k's appearing exponentially. These should all be kept together. And conversely, you have stuff like this that's just, carrying members of the community.
But why are we separating Fn k plus 1 into 2 components?
So look at Sn plus 1. Is it hard to figure out the behavior of that as n goes to infinity?
Oh, okay.
And in fact, that's going to converge to the normalization constant of a Gaussian.
Mm-hmm.
That's why we pulled it out. So that's a good question to ask. There is a method behind all the algebra.
Okay.
But the problem is finding a good path through the algebra. All right. So the next thing is, we've talked about this, I think, briefly before. Whenever you see products, you should be thinking logarithms. Logarithms are phenomenal. They can convert multiplicative relationships to additive ones. And so what we want to do now is we want to expand this n minus k. We want to introduce a new variable x to take the place of your name. So we can rewrite k, the number of steps, as essentially the mean value plus x copies of the standard deviation. And now we need to do some work to expand the log, log of k. And we tried to write it in this way and then this way. We showed that the mean is about n over 2. And we showed that the standard deviation is of size square root of n. So if n is very large, then the only values of k where there's an appreciable probability are those k near the mean. And we measure nearness by using the standard deviation. So it's how many standard deviations are you away? Hopefully it will be no more than 3 or 4. But now we have to figure out what is the log of k, what is the log of n minus k. Well, we have our formula for k. We plug things in and we just do a lot of algebra. Here we can write the log of a product as the log of n minus the log of 2, and then the log of 1 minus x over root n. So now we just feed all of the stuff in. And so we can approximate the log of 1 plus x over root n, the log of 1 minus x over root n, and we get the following. We approximate further. Now, I am not envisioning you doing stuff like this for your project, but I wanted you to see what we were doing last year. And this is the setup. This is the two-dimensional case. There is a better framework for the general case, but I don't really want to get into it. And so when the dust settles, we got a formula for Gaussianity. So for future work, and then I want to use the rest of the time to just discuss what you're looking at. We had somebody last summer who tried looking at gaps, but didn't get far and moved to one of the other projects. Last year, we tried to find a combinatorial formula for the number of simple paths in higher dimensions beyond 2. We had to give up, sadly, in failure. And the last, which most people worked on, either initially or by the end, was to prove Gaussianity. All right, so for you guys, I wanted you to look at gaps between summons. I wanted you to look at the distribution of gaps. You've got to tell.
You mean the first one?
The first one.
Do you mean?
So someone started looking at it but didn't really get far.
Oops.
So we now have pairs of indices. And you have to tell me how you're going to measure a gap. So let me see if I can punch up the slides from last time. Okay, I'm loading up the slides from last time. Okay, here we go. Okay, you should be able to see lecture 3 now. Correct? Can you see lecture 3?
Yes.
Yes.
And this is what I wanted. I wanted a picture of the lattice so that we can talk about, say I go from here 4966 to 296 to 10 to 2 to 1. You need to tell me how to measure gaps.
Well, I think there are two methods. The first thing that bumped into my mind is like using Pythagoras theorem to measure the real distance. Like
good. So one thing is if I give you a pair, convert it to a real number using Pythagoras. Excellent.
But I mean, sometimes, the distance that's calculated by the gap that's calculated by the Pythagoras theorem is very rare, and we might not get like a decent distribution. So I think we can also adopt another method, which is to plus the gaps like in the x-axis and y-axis to form a new gap.
So, okay, so just add them. So that is another approach as well, is to say that, look, if I have a gap, 3, 4, so let's say I start off at 1, 1, 2, 3, 1, 2, 3, 4 to go to 15, 22. One thing is to say, well, the gap is going to be the square root of 3 squared plus 4 squared, which is 5. Or the gap is going to be the wait time between one summand and another. And so if I'm going from 3, 4 to 0, 0, my gap might actually be an ordered pair 3, 4. And the third one that was suggested is to use Pythagoras, that the gap is going to be the square root of 3 squared plus 4 squared. So one idea is to use Pythagoras, one idea is to just sum them, one idea is to keep it as an ordered pair. Which do you think is the right definition? So one way to look at it is, which one is going to give you the most number of things amalgamated to being said, yeah, they're the same distance. They're the same gap.
The first one, I think.
Which is Pythagoras?
No. To sum up the x and y.
Yeah, so if you sum up the x and the y, a gap of length 3, 4, or 5, 2, or 6, 1, or 1, 6 would all be the same length. So if you use that approach, you are likely to have many things amalgamated and called the same gap. That might actually be a good thing. Sometimes you need to have a bunch of elements so that you can average over them or sum over them. What if we used Pythagoras? What if we used the square root of the sum of the squares? Would that compress things? So if we use Pythagoras, would a lot of different gaps be now considered the same?
No.
So every gap would be unique. Logarithms of numbers, two numbers that differ don't become the same after a logarithm. Is it possible, if I use Pythagoras, the two gaps that were initially considered different could be mapped now to the same quantity?
Yes, the gap between like 1 and 38 is the same with the gap between 1 and 22.
What?
I mean, like if we use this, like the gaps between two numbers will be considered the same for like multiple ways. So.
Well, right now we're talking about using Pythagoras. So that if you have a gap that's the pair 3, 4, we'll consider the square root of 3 squared plus 4 squared.
I think I understand his point. He's pointing out like if we pick, if we include 38 and 1 in the decomposition, then it's the same as including, the gap is the same as including 22 and 1. Like
I'm sorry. You're doing 38 and 1 like this, yes, and 22 and 1 like this, yes.
Yes.
38 and 1 is a gap of size 1, 2. And 22 and 1, this is going to be a gap of size 2, 1. So 1, 2 and 2, 1 are going to have the same hypotenuse by Pythagoras. So when you try to use campus resources, you're going to run into the same problem. So this identifies differences or gaps that were initially considered different are now going to be considered the same under this equivalence. So that's a defect of Pythagoras. It's a different defect than adding the x and the y components. The other thing we can do is we could just keep the distances as ordered pairs alpha comma beta. And different people will different gaps will be considered the same now. So going from 38 all the way down to 1, 364 all the way down to 1 is probably the same as going from 342 down to 2 and then to 1. So we have three things. Pythagoras, so let's take the square root of the sum of the squares of the components. We have add the x and the y components. And then we have just leave it. Just leave it as an ordered pair. And just count how many ordered pairs do you have that are 1, 0, or 0, 1, or 3, 4. So there are three people on the phone, and there are three things to look at. Now, I think we have at least one other person in the group who's just not able to call in right now. But the goal was to get to the point where after the fourth lecture, you are all clear on what a good research project is. So does everybody have an idea of what the three different gap projects could be?
Yes. Probably.
So now it's time for you guys to choose which of the three metrics do you like the most. And again, we have some other people, they can come in later. If multiple people want to do the same metric, that's fine. But you want to go through and you want to start calculating, how many gaps do you have of length? If you're adding things, 7, for 3 plus 4. If you're doing square roots, it'd be 5. Or if you're just leaving it as a pair, 3 comma 4. And this way.
So are we going?
Yes.
So are we going to choose among the three?
Well, you should all talk amongst yourselves and copy me on the conversations about which definition would you like to look at. And if multiple people want to look at the same definition.
Okay. Are we going to discuss it now or later on?
No, I want you guys to think about it. Don't just have right now. Spend some time thinking about what you would like to do, and then you can include me in the emails or not. Talk amongst yourselves and see who wants to do what.
Okay.
And then start counting. So the easiest thing might be gaps of length 1, or gaps that are 0, 1 or 1, 0, depending on what problem you're looking at. And then start to see if you can generalize the result that I did with my students years ago, where we proved that the distribution of gaps was a geometric decay, and for the Fibonacci numbers, the decay constant was related to the golden mean. The goal would be for you guys to try to get something like that in a two-dimensional setting, which is going to be much harder. But good problems are often hard. So does this give you a good sense of where things are and what to look at?
I have one question.
Yes.
So are we going to how do you say, try to decompose a number in an interval, or we just?
Well, what's nice is it doesn't matter what the number is anymore. All that matters is you just put a bunch of points and have a valid decomposition.
But if we don't know the interval, then we don't know, we don't have a sense of how the difference between the origin and the number we want to.
So assume you're always at the corner n, and you have to have that as your first summoned in your decomposition.
It must be n rather than like a and b. So like the
Right,
x and y
do
must be
do the simple case first where the two components are the same.
okay.
And then again, if you have any other questions, just shoot me an email. All right. So again, talk amongst yourselves. Feel free to include me as you try to decide which project you want to do, which metric, and then it'll be interesting to see what are we able to prove in these different settings. All right. Have a great rest of the day. Take care, all.
Good night.